In section 2.6, we're looking at proof statements about segments and angles. So this section is our first venture into looking at actual geometric proofs. So while the emphasis, we don't have too much new information, but the emphasis is going to be on getting used to that process, which is proofs. So a couple things to mention. A proof is a logical argument that shows the statement is true. Your book will typically show it as a two-column proof, as listed here. We talked about algebraic equations yesterday. So you could write your steps out to solve and then your regions to go with it. And if you look in 2.5, we talked about addition, subtraction, multiplication, division. We would list those reasons along the two-column proof. We're going to demonstrate more of a flowchart proof today as we go through these. It keeps things a little bit organized so you can maybe see the process as it goes a little bit better. But it can always be copied back to a two-column proof. Why we're doing this is because we're looking at theorems, and a theorem is a statement that needs to be proven. So once it's proven, we can, in fact, use it as fact. This is different than a postulate. We've had postulates so far, and postulates are just a given statement we accept as true. A theorem, we have to use our prior information, or our prior knowledge that we have, to form that logical argument to prove it, and then we can actually use it. So the first theorem we actually have is the congruence of segments theorem. And this said segment congruence is reflexive, symmetric, and transitive. This looks very similar at first to one of the definitions we had in the previous section where we looked at reflexive, symmetric, and transitive in terms of equality. We said we could use it for real numbers, segment length, or angle measurements. Now we're looking at congruence. So 2.5, it was equality. Now we're looking at congruence, but since this is a theorem, we now have to prove each of these statements do exist. So this one is actually three different proofs. So we're going to go one at a time. I can probably fit reflexive down here. We'll talk about when they're if-thens, we actually are given what we need to start with and we can figure out what we need. For this one, we're actually starting with AB is a line segment. And they just say for any segment AB, so we're given that. That's our first step. Anytime you have a proof, you always want to state your given first. AB is a line segment. That's what we're talking about. That's what we're going to use. Now, we know if we have a line segment, this is different than this. This means the length. So we could say the length AB is the length of AB. And that was where we can measure it, we can give it a value, and that goes back to Chapter 1, our ruler postulate. Now, I am now looking at length. We go back to yesterday, or 2.5, depending on when you're watching this. We go back to 2.5, and we could say that AB is equal to AB because it was the reflexive property of equality. So that was back in equal. Look at it equal. We want to get it to congruence. Now this actually brings up a very important definition we're going to use. It's a very important tool for us. It lets us say that if something is equal, the lengths are equal, if the measures are equal, then the objects are congruent. It also, we'll find later, lets us jump from congruence to equal in the other direction. And this one is the definition of congruent segments. This is a big one. We'll even write it up here. Definition of congruent segments. It allows the jump between equal and congruence, back and forth. So I'm over here talking about equal. I want to get to congruence. I can use that as a reason. Even if it was the opposite, which we'll see soon, I could do the same thing. And this we're going to see in this and later on is a common theme because right now I have congruence in all of these statements. I know they work in equality. So if I had a way to go to equality, verify it's true, and then come back to congruence, I could make these proofs pretty easily. That's the goal. That's the important one right there. Of all the tools we use, this is one of the important ones, probably in the top 5 of the ones we use most often. So next one is symmetric. So for symmetric, I have if AB is congruent to CD, then CD is congruent to AB. This if hypothesis is our given, and that's what we're proving. So for symmetric, we're given that AB, so segment AB is congruent to segment CD, and we need to prove segment CD is congruent to segment AB. I'll put that other paper off to the side. That's what we're proving. So anytime we have a proof, we write our given first. AB is congruent to CD, and we want to get to CD is congruent to AB. Now, sometimes we can look at a proof and kind of talk our way through it. If I took a congruence statement and I flipped the values, it would be this one. That is what symmetric property is, but we can't make that jump because that's what the property is telling us, or that's what the theorem is telling us. We can't use the theorem as the reason for the theorem working. We have to use the prior information. Now, going back to what we did in the last section, if I would have made these equal signs and said their lengths, I could have switched them. So we're going to do that. So I'm going to jump from congruence to equal and say that AB is equal to CD. Oh, forgot my given here. Now, what lets me jump from congruence to equal? The definition of congruent segments. Okay, now those are equal. You know, if those are equal, we can flip their order. CD equals AB. Reason for that was the symmetric property of equality. Now that it's equal, it looks just like this. The only difference is this is equal, this is congruent. We can jump back by the definition of congruent segments, and we have our answer. So, we're in congruence, we jump to equality, flipped it using symmetric, and jump back to congruence. We have our proof. Now, I mentioned two-column proof earlier. If I want to make this into a two-column proof, I could just number these, and it would go 1, 2, 3, 4. Write them in, AB congruent to CD, on and on and on, down to CD is congruent to AB, and then list the properties as they match, given definition of congruent segments, on and on and on, and I'd have my two-column proof. So this even gives you a way to map it out, kind of give you a process to it, and you can always copy it back to the two-column proof. Last one, we'll use on the bottom of this paper here, is transitive property. So transitive, we have, all right, segment AB is congruent to segment CD. Segment CD is congruent to segment EF. Then AB is congruent to EF. Transitive property, hopefully we're realizing that it has a common value in both congruence, or both equality, we looked at yesterday. Those values, if they're both congruent to CD, they're congruent to each other, which is essentially what transitive property is going to do for us. They're both congruent to CD, they're congruent to each other, so AB is congruent to EF. So, we're given these two statements, we need to prove this one. Let's copy that in. So, given okay, let's start with what we know. AB is congruent to CD. CD is congruent to EF. Both given. We want to get to AB congruent to EF. So our common theme so far is change it to equality using that definition, do the property, change it back to congruence. We're going to do the same thing here. So I'm going to say if they're congruent, then they're equal. And that's the definition of congruent segments. And I'm using those arrows to guide it. I got this piece of information from that term, this piece of information from that term. I'm not going to draw the arrows randomly. I want it to connect so I can also see the process. And we're going to see that later on, how that does, how the arrows will also help us. But here I am, okay? They're both equal to CD. So that means that AB equals EF, because they're both equal to CD. So I got that from both of these statements. The way we did that was transitive property of equality, which very close. Right to the end, we have to jump from equal to back to congruence, and that is our definition of congruent segments. Oh, ran out of the screen there. So, we work through kind of this similar trend with symmetric and transitive. Go to equality, do the property, come back to congruence, and you have your answer. Now, if anything, the goal on this proof was to see that that definition of congruent segments is a very important one, and we're going to see that further on as well. Now, we have another theorem, the congruence of angles. It's basically the same idea as we just looked at. The angles are reflexive, so I could say angle A is congruent to angle A. Symmetric, if angle A is congruent to angle B, then I flip it, angle B is congruent to angle A. And transitive, if angle A is congruent to B, if B is congruent to C, then A and C are congruent. It's the same process. We're not going to go through the theorem or the proof to it. It would be the same process, though, if we did. And you're going to see a common trend of switching to congruence to equality, equality back to congruence. Now, what lets us jump here is the definition of congruent angles, or maybe called definition of angle congruence, and that lets us go as well from equality to congruence and congruence to equality. So that's an important one for angles. You wouldn't call it the definition of congruent segments when you're talking about angles. So just make sure you identify it the correct way. So let's look at a couple proofs. Anytime we get a proof, we should label what we know. I know RT is 5, RS is 5, and I know that RT and TS are the same. What I want to prove is that RS and TS are the same, or that they are congruent. Now, before we start the proof, we're trying to get that basic understanding of working through the process. Maybe it's a good thing to just stop here and see if you can kind of explain your way through it. Maybe it's not using all of the exact terms, but if you can kind of think through the process, you kind of get used to it, and you can fill in the gaps and fill in the necessary information as needed. So I look at this one, and I see, well, these two are connected, they're congruent. These two, they're connected, they're equal, same length, so they could also be congruent. So what I want, RS and TS, both have some connection to RT, whether it's congruence or equal. So the fact they both have that connection means they would be the same too, and that's that transitive property idea. So we can't directly do that and just state it, but that gives us an idea of what we're going to do. Transitive property is going to help us get there. So let's start with stating what we know. RT equals 5, RS equals 5, RT is congruent to TS. Our reason for those is they're all given. What we want to get to is RS congruent to TS. Well, let's see. We got congruent here. We got congruent here. These are equal, though. So maybe we can do something with these and get these to congruent. Well, I can't say RT is congruent to 5 or RS is congruent to 5 because congruence doesn't deal with numbers there. But I notice they're both equal to 5. Well, if they're both equal to 5, I know that RT equals RS. If they're both equal to 5, they're equal to each other. And that is transitive property of equality. Okay, so now I have two terms. I said I wanted congruence. I could change those. Let me draw my arrows here. Both of those led to that step. This new step is going to be RT is congruent to RS by the definition of congruent segments. So I've taken equal, done some work with it, and got it now to congruence. So congruence, congruence, congruence. Now I want to look if I can connect those. And I said earlier, transitive idea may be the key. Well, let's see. RT is in both. If these terms are both congruent to RT, then they're congruent to each other. They both have RT, so I could say that RS is congruent to TS, which is what we want. So really I can just connect these two statements and say that by transitive property of congruence, I get that they're congruent. That's my proof. I've created that logical argument on how to get there, and I'm done. Now, I want to make a 2-column. I could number them 1, 2, 3, 4, 5, 6. Draw my 2 columns, list them out, and I have it all completed. Now, you could make it 1, 2, 3, 4, 5, 6, or piece it together, but you want to make sure it does follow a logical flow. If you have an arrow going down to something, you don't want to list it before what's above it. But we list it out, we would have our proof. Okay, if you don't see it, or maybe you do see it, maybe jump back in this video to the very beginning and see if it makes sense what we did and worked our way through it. And it's just understanding that process, something we have to get used to. So now we're going to look at one with angles. So I'm given AOI, which is this, and EOU, which is this. Those are the same. I want to find that 1 and 3 are the same. So, do you see how you can work to it? Again, maybe it's not knowing all of the terms, all the steps to it, but if you can logically see the process to show that they're the same, not just saying, oh, they're the same, they're equal, no, but see that process, that's the important part. When I look at this, I see this piece and this piece are the same, but they have 2 in common, this overlap. So if they're the same and I was to get rid of this overlap, what's left would also be the same, which is what I want. So I'm going to try to work towards that. Now, if I'm not quite sure how to make that step, well, I can at least start off and see where I can go. Always start with my given, and I want to get to the measure of angle 1 equals the measure of angle 3. Realize we don't know that reason yet. That reason to get there is our last step. So, let's see. I have letters here naming them, but this is numbers. Maybe I can rewrite this in terms of angles. So AOI is actually 1 plus 2. So if I wrote the measure of angle AOI equals the measure of angle 1 plus the measure of angle 2, that would be a true statement. Now, what lets us say that is a property we looked at, or a postulate, I should say, we looked at back in the first chapter, and that was angle addition postulate. I can add the parts, set it equal to the whole, that works. So it's kind of bringing in that concept. It's not directly using it here, it's not something we've talked about today, but we have to pull in previous information. Now, same idea for EOU. The measure of angle EOU is the measure of angle 2 plus the measure of angle 3. And again, angle addition postulate. So that got me to those 2 statements. So now I can write them as numbers. So I want to replace AOI with 1 and 2 and replace EOU with 2 and 3. So to replace, we call that substitution. So it's going to be the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. And that's substitution property. Substitution property of equality. But now we're close, because now if I look, 1 plus 2 equals 2 plus 3, and I want 1 and 3. We mentioned a property yesterday, and we mentioned a little bit today, that reflexive property is when we set something equal to itself. And that's when we can use here. Because 2 equals 2, I can subtract it from both sides. And even if I ignore that, well, 2's on both sides. I want 1 and 3 together. I can subtract measure of angle 2 from both sides, it allows that, and get to that, and that's by subtraction property of equality. So I've even worked through that process, kind of what I did. I said, well, here's the angles I have. I rewrote how I looked at them. Here, I said, well, 2 is in both of them. I can subtract it. Left me with the same thing, and that is my answer. Okay, maybe on this one again, go back, see if you can watch it from the beginning, and you can see that process even before we work through the proof. Practice them. The more you see them, the more you see things in common. If we do reflexive, which usually is a subtraction or addition following that, we can use angle addition as well as segment addition to break things up to lead to substitution. Certain properties, certain rules do show up and they do repeat themselves through there, and it's just understanding the pattern of the proof as a whole, and even understanding the pattern that the kind of small sets of properties do fit together.